In this video, we're going to talk about how to change or adapt our word search plan into an actual implementation. Let's talk about this function that we've defined. We've got our word search function, and for each starting place, basically, for row in length of board, right? And then for call in length of board, and I need to make those ranges. Range. So we've got our loop here. Now I know it's a double loop, and usually that's like not good practice usually when we see a nested for loop, but we do have to check every starting position on this board. So it's really O of n, this specific thing, because we have a 2D array. Please take note, don't call this, X and Y. A lot of times people call this X and Y, and they're really not. This is not X, because X is the horizontal and Y is the vertical. And if we loop over our 2D array, we're really looping over each row and then each column. And so if you do X and Y, you're going to be flipped, and a lot of confusion comes from this. So we've got our search, right? And let's imagine that we just have a searching function. So we've kind of got our for each starting place, right? Thing up here. And then what we want to check to see is at the board of row and column, right? We can say if the board at row and column equals our word at 0, the first letter of our word, then we know that we should start searching for things here, right? Otherwise, we don't have the right thing. We don't want to start at A because we know that it's not the right solution. So we've got our is the letter the correct beginning letter, right? So that's handled. So if it is, then we want to start a search at this point, right? Now, if we look at our plan calls itself. We have start a search at that point for each possible place to check, is it the correct next letter? If so, search at that point given the next letter. If not, back up to the next known good letter. So there's a few problems here. We've got a sort of searching algorithm that needs to call itself. So what I'm going to do is define a function called search. And our searching algorithm is going to be needs a little bit more information. We still need the board and the word, B-O-A-R-D. There we go. But we also need to know what is our prefix? Like, what have we found so far? And so in this search function here, I'll go ahead and just move this up here. So to start a search, whoops. There we go. Cool. So to start a search at this point, we want to say search, right? We want to say this board, S-C-A-R-C-H, this board, this word, and then we want to say, what is our prefix? What have we found so far, right? Because this search algorithm, since it's going to be recursive, we have to pass in what have we found so far. So this is where we're going to start that search later. We want to basically say, start in the right place, right? So we need a prefix. And then another thing that we have to keep track of is where are we currently in the search, right? So if our position, our current situation, row and column, I'm just going to pass that in as a tuple, row, call, right? And we also have, let's see, prefix equals word at 0. And then we pass in that prefix, right? We want to put in where are we finding it so that our search knows that we're starting at this C and not that C, right? And then, so that's going to be called position. And then the last thing we want to do is keep track of stuff we've visited already. So visited is going to be a set of places that we've been. So it's going to be a set, a literal set, right? So that we can just add a bunch of tuples of places that we've been, and we can easily check to see if we've been at a place, right, in this specific search. In this set, we'll put our current position row. Oh, sorry, no. Yeah. So we'll just say visited dot add our current position, so that we know that we've been there. Okay, so we're starting a search. Whoops. There we go. Yeah, we're starting the search at this point. Cool. So the next thing that we need to do is find every possible place that we could check, right? And wouldn't it just be really nice if we just had a list of places that we knew to check? And so for this, we're actually going to say get candidates is a function, right? We'll say DEF, there we go. And now what get candidates needs is it needs the board. It needs the next letter that it's searching for, right? I believe we need the position that we're in right now, so all the possible next positions, and we need to know whether we've visited something before. So we'll keep those. I'll just add some spaces in here so it's easy to read. Whoop. Cool. Cool. Okay, so the next thing that we need to do is find candidates, right, to check. And so what we need to do is check a bunch of different locations. So if the so let me get the row and the column from position. And this is destructuring, so we're basically taking that tuple and turning it into two variables here. So now what we want to do first is we want to say if the row is row plus 1 is less than the length of the board, right? So we don't want to go outside of the board. Then we can check to see if board at row plus 1 at the current column, right, equals letter. That's the letter we're looking for, okay? So what that'll do in this first one is, given a position of 0, 0, right, and being told that we want the next letter in word, right? So when we do search, we will call get candidates. So for candidate in get candidates, right? Now we're giving get candidates just gonna, the board, the position, right? And then the next letter in the word that we want. So we want to get next letter is word at the length of prefix, right? And so if prefix is one letter, then we'll get the next letter, we'll get an A, right? So if prefix is C, then our next letter is A, and so our length will be 1. So our next letter is something that we need to get, right? And then we also need to pass in the visited set. Okay, and so we've already told the visited set to have the position that we're in. And so if the board one row down, for example, up here, C to B, right, is the letter, and then we also want to only check that if let's see, sorry, it's it's row plus 1 comma call, not in visited, and this is the letter. So first we want to check, have we been in this place before? And if not, then we check to see if this element is the letter that we need. If so, candidates dot append our current next position. So row, let's see, sorry, columns, row plus 1 comma call. Okay, so that's a lot of work just to check the next letter, right? It's a lot of different conditionals that we need to check. And that's why we encapsulated this in a function, right? It would be a big pain to have to see all of that in our searching algorithm. So we'll do this again, and then we'll do it with -1. And if the row is greater than, row -1 is greater than the length, or sorry, is greater than -1. And that just keeps us from trying to check above when there is no space above. Like if we're checking this A, we don't want to try to go up because that's the 0th row. And so as long as row -1 is bigger than -1. And so then we'll translate this row -1, -1 here, and then -1 here, minus, there we go. And so as long as we've got some sort of guardrails around this, we can add that as a candidate, right? And so I'll just do this again, but we want to do it with column. So call +1 is greater than or is less than the length of the board, right? I'll change this to call, and then this is row, column -1, row, right? And so this is kind of a lot of work that you have to do. There's no real way around this. There's like some things you could loop over or whatever, but that's all really premature optimization. When you're just trying to solve something like this, that's really what you want to do. Sorry, this is called +1. Yeah, sorry, +1. Messed that all up. Call +1. And this is why also you want to do this in one big spot where you're just manipulating directions, because it's very easy to mess this up, right? When we're operating on planar coordinates and we're doing it in this systematic way, you end up with one of these functions where you have a lot of the same if statements and it's repeated over and over again, and maybe it seems like you should be able to somehow not do this or do this with some elegant thing, but honestly it doesn't matter as long as this function is helping you, right? that, and it's easy to read. Like, you can see that you're checking the 4 directions, and if you need to do something like to extend this to check all the diagonal directions, it's really just copying and pasting and manually checking those diagonal directions. You can loop through a list of translations, but honestly I found that a lot harder to read, so it's harder to like debug when you need to debug it. So we'll check all the candidates, left, right, up and down, right? And if so, we'll loop over those candidates, right? So this is just going to be a list of places to check. And so that's, is it the correct next letter as well, right? So we ask ourselves, you know, is it the correct next letter? And we only return a list of places where it is the correct next letter. And so if it is the correct next letter, which every candidate in this list that we get returned is the correct next letter. So we can say prefix plus equals next letter. Okay. And then if so, what we do is we say search again, right? With the same board, the same word, the same prefix, but we've mutated this prefix, and what else goes in? Position, and so the position is going to be the candidate, right? And that's the next position from which we're going to search. And then we want to keep track of visited, right? And so because we're calling search, once we call it on C, for example, this C, then it has to go look at all of the next candidates, and it'll return this A, right? And so we need to know that that's in the list of visited, and so we add that, and our prefix becomes CA. And then so the next letter is word at the length of prefix, which is 2 now, and that will give us the last letter in the string, and that's T, right? So the last thing that we need to do is we need to kind of add our base case here. So when do we stop? It's either when we found it or we didn't find it, right? So if word is prefix, right? If word is prefix, then we return true. But if we get to the end of this, what we'll do is we'll say found equals search, right? And if found, return true, so that we're recursing up out of these. But otherwise, else, if it's not found, then we want to return false. But we also want our prefix not like to be less. So prefix equals prefix, at from 0 to the last letter. We just basically take that off, and then return false, right? So I think that's everything. Let's see. Oh, and then we also need to remove the visited candidate. So we just need to visited dot remove position, right? Our current POSITION. Is it correct? Yeah. Okay, cool. And then we return false because that didn't work, right? So let's actually run this and see what happens. Okay, unexpected indent. I'm sure I have some unexpected indent in here. Where are we at? 46. Oh yes. I don't know why that indented. There we are. Okay. So we run that. And we get nothing because our word search doesn't. So I'll just say found equals, and then at the end, if found, return true. If not, we want it to keep searching, so we're not just going to return found, and then we just say return false if we get all the way through all of the starts and we never find it. So this should return true in all cases. Oh, we're not printing. Print. Whoops. Yeah, there we go. Cool. And then we run it. And it should return true in all cases. The last one, it's not working. So let's investigate why that is. So let's, in the search, since the first two, it's finding these fine, I'm just going to go ahead and comment this out. Now, it should find it in the previous one, but let's make sure. Let's see, call minus, minus, plus, minus, plus, minus. Okay. Plus, minus, plus, minus. Great. Okay. So then I'm going to print visited. Actually, I'm just going to print the position. And so we're going to see a lot of positions here. And let's see, 0, 2, and 0, 1. Okay, so then we start a search. And the only place on this third one that there is a C, here is 0, 2, and then the last one is 0, 1. Okay, so do we, oh, you know what? I'm realizing we need to go to the very end, and that might be the problem. Oops, plus 1, plus 1. Let's run it, and it should come up true. Hooray! So these are all the start positions that it found, and all the start positions that it kept checking, right? So when we print that position, I'll print the prefix as well, and that might illuminate kind of how that's running. So we get C, and then we get CA, and then we die, right? And we get C, and then we get CA. And I think on the last one, it just doesn't print that because it finds it, by adding this. So I'll just say print prefix here and position. Yeah, we just never get to this print statement on the third run. Cool. Now we'll do the third run, and it should show. Cool. So yeah, so then we get C, we get CA, and then we die off, and then we start at 2, 3, then 2, 2, then 2, 1, and then we get true. So that's how we solve this problem, and as you can see, it's several smaller problems wrapped up into one. How do we get to the next spot? Which next spot should we check? And down here, this is really where the backtracking happens, right? And this is what prevents us from exhaustively checking every possible combination. We're only checking the next best step, right? So, yeah, hopefully this was helpful, and thanks very much.